Okay, so extending on from this content, what we're going to do is look at, it's probably the last type of beam balancing question and forces question like this. The very first part of this whole thing, where I talked about the example of, you know, what a free body diagram is. We talked about a bridge with supports, and that we would arrive at this type of free body diagram. This is a standard exam question where they give you all the distances in one force and you have to calculate the two reactions. So let's go ahead, I'll show you how to do a question like that now. You can only do this question if you understand the concept of the three conditions for static equilibrium, and we've already covered how the sum of verticals works and the sum of horizontals, because they work the same, and then we've spent a fair bit of time doing the sum of moments. So now that we know how all three of them work, let's do a complete question in a structure like this with this type of free body diagram. So I'll give you a setup and I'll talk you through it, and then I'll do a worked example, and then I'll give you a bunch of questions to do on your own. So we start off with creating a valid free body diagram. Let's get that and make it black instead, and a wee bit thicker. Right, so there's a beam. So in these instances it tends to be that there is a downwards force and that there's two reaction forces pointing up the way. Okay. And they would be labelled something like R1 and R2, or RA and RB or something. 62 kilonewtons, right? And then they would give you a distance as well. They give you a couple of distances, so I'll tell you that one. 4.0 meters. Might tell you the distance of the total span. Let's call that 32 meters. So this question would be calculate the reactions R1 and R2. Now that's a complete question. They tend to break it down. They might go by taking moments around R1 calculate R2 or something like that, because that's what we're going to do. In order to calculate R2, we pretend R1 is a fulcrum and we just balance that beam, and that will tell us what R2 is. We could do the same for R1. We could take moments around R2 to work and balance the beam to find out what R1 is. So if the question is calculate the reactions, then what you're going to do is you're going to pretend one reaction, doesn't matter what one, is a fulcrum. Take moments around it, or sorry, balance moments around it. Balance moments around that fulcrum. And that way you calculate the unknown reaction. You could do that twice, or you could then do you could then balance vertical forces to find the remaining reaction. Okay, so let's do these in order. So we're going to pretend that one of them is a fulcrum. So let's say I'm going to take moments around R1 to calculate R2. That means I'm pretending that R1 is a fulcrum. I've got R2 out here, and I've got 62 kilonewtons in there, and that's 4 meters and that's 32 metres. Yeah, so I've just replaced R1 with a fulcrum, and I can now balance that. I've got this unknown force. So the sum of the anti-clockwise moments must equal the sum of the clockwise moments. So the anti-clockwise moment, there only is one, R2 multiplied by 32, and that must equal the sum of the clockwise moments, which is 62,000 kilonewtons there, multiplied by 4. R2 equals 62,000 multiplied by 4 divided by 32. So R2 equals 62,000 multiplied by 4 equals that divided by 32. 7,750. 7,750 newtons. Okay, and I round that to the correct number of significant figures, which in this case, because of that, oh no, my original data was 2, 2 and 2, so it's 2 significant figures, so that's 7,800 newtons to 2 significant figures. That's me worked out R2, so I've done that. I've balanced the moments in the fulcrum, balanced the vertical forces to find the remaining reactions. Yeah, so right now I know R2, I now know that this is 7,800 newtons. I don't know R1, so of the three I still look for R1, so I can now do one of the other conditions for static equilibrium. All the upwards forces must equal all the downwards forces, so that's going to be R1 plus R2 must equal 62,000. So R1 must equal 62,000 minus R2, which is 62,000 minus, now it's important that you use the unrounded value. When you carry values forward into another calculation, you shouldn't use the rounded one, you use the unrounded one. 7750. So 62,000 minus 7750, that's 6,200 minus 7750, 54,250. 54,250 newtons, and again down to two significant figures would be 54 kilonewtons to two significant figures. Right. So given this type of diagram at the start, we can use sum of moments around one end to calculate the other reaction, and then we can use the sum of verticals to calculate the remaining one. I could do the sum of moments twice. I could take moments around R1 to find R2, and then redraw the diagram again, moments around R2 to find R1. I would get the same answer. So this is standard examination question. Okay, this has been in nearly every exam for the last 5 years. So you need to have these skills to do well at that part of Engineering Science National 5. Okay, so what I'll do is, again, I'll create just a wee bunch of maybe 3 or 4 questions and ask you to do the same thing again. Right, okay, let's do that. Right, okay, so these are the 3 questions I want you to do. The first one is just almost identical to the one I did. What I'm going to do is I'm going to add in just a little detail. Find RB first. Alright. In this one, I'm going to say find R2 first. Now, this one's slightly different because the way I've laid the distances out, you'll need to be careful when you do that moments part that it's always a distance to the fulcrum. Don't just use 4, 5 and 6 because you'll need to add things up to get it right. And in this one, I'm going to say find R1 first, forcing you to recalculate all your distances. Right? Find R1 first. Now go ahead and do that, and we'll see how you get on. Thank you.